Hello, this is the first of a series of warm-up videos designed as preparation for the second paper of the IGCSE chemistry in the summer of 2016. So these questions are specifically for paper 2 and cover things that weren't seen or didn't crop up on paper 1. So you can see that these are the ones that we're going to go through. So it makes sense before you watch any of these videos to download the PDFs, which I'll put on the website, and do the questions first, and then to go through to see if you get the answers. Okay, so let's get started with some electrolysis. Now this is quite an old question, it goes back a number of years, but it's definitely still relevant and is something you should have seen in the lab. I apologise for any background noise. I'm doing this in a room next to quite a busy road. So we're using lead 2 bromide, and lead 2 bromide has the formula, I'm hoping you know this, of PbBr2. Bromine has a valency of 1, lead has a valency of 2 as we're told, so swap them over, PbBr2. And we've got the lead bromide in the beaker, we're heating it to melt the lead bromide, and it says here that we're using copper electrodes. So why do we use copper electrodes? Well, copper is a good conductor. Why does copper conduct the electricity? Because it has delocalized electrons which can move. And it's really important you say these delocalized electrons can move. Now when you initially set this experiment up and the lead bromide is solid, it doesn't, no electrolysis takes place. So quite often I set this up with a lamp in the circuit, somewhere about here, and the lamp doesn't come on. And as you continue to heat it, or as you heat it, eventually the lamp comes on, and that's because the lead bromide will only conduct when molten. So why is that the case? Well, when it's solid, the ions cannot move. So no conduction takes place, ions not move. Okay, when it's liquid, the ions can move and they carry charge. And I apologise for my handwriting, the stylus I'm using is absolutely terrible. Here we've got the positive electrode, here we've got the negative electrode. So where would the lead go? Where would the bromide ions go? Well, the lead ions are positive, so they're going to be attracted to the negative electrode, which is here. So we will get a layer of lead building up, or perhaps even, actually it'll probably be at the bottom because lead's pretty dense, so it'll sink. So the lead will be at electrode B, okay, and the bromide will be at electrode A, and I can't quite fit it in the box due to something on this program which doesn't allow me to write at the bottom. So we'll get bromine appearing around electrode A, and bromine at room temperature is a liquid. However, this reaction is being done at quite a high temperature, so the bromine will probably evaporate off. So you'll see sort of brown fumes coming off around electrode A. So it'd be a very good idea to do this experiment in a fume cupboard, so you're not breathing in bromine fumes. Now you can see here that the lead is gaining electrons, and a gaining of electrons reaction is a reduction. Reduction is gain. Okay, so you should probably have used oil rig. Oxidation is loss, reduction is gain, or I must admit I prefer Leo Ger, simply because that's what I was taught at school. So Leo Ger, losing electrons oxidation, gaining electrons reduction. And so if the lead one is reduction, the second reaction is oxidation. And on we go. to look at a moles question to do with electrolysis, and it follows on from the reaction we've done. Now you do need the equations, which are on the previous page, so I'll just add those now. And it tells you that the amount of charge passed was 0.1 Faradays. Now a Faraday you can think of as effectively it's just telling you the moles of electrons. So moles of electrons equals 0.1. So if I have 0.1 moles of electrons here, the moles of lead, well, the ratio is 2 to 1. So I'm going to have half the amount of lead. So moles of lead is going to be half 0.1, which is 0.05. And what about for bromine? Well, again, the ratio is 2 to 1. So the moles of bromine are going to be 0.05. And the question then finishes with calculate the mass of bromine formed. Well, we've got the moles of bromine, so we need to convert moles into mass. So hopefully you're remembering the equation, moles equals mass over mR, or you might be remembering the triangle where we had moles, mass, mR. So we'll have mass of Br2 equals moles times mR. And now you need to find bromine on your periodic table, which I hope you've got in front of you, because you should have that in front of you for all revision. And we know that the moles 0.05, and you're expected to be able to calculate the MR of bromine. So if you find bromine on the periodic table towards the right hand side, it has an atomic mass of 80, so Br2 has an MR of 160. Okay, and if you work that out in your calculator, you find that you produce 8 grams of bromine. Now this question is asking you to describe how you would carry out a titration, but it's very important you take on board what you're told in the actual information up here. You're told you take 10 centimetre cubed of sulfuric acid. Now in a titration you would measure that with a pipette, because you could get a 10 centimetre cubed pipette. So you pipette 10 centimetre cubed of H2SO4 into a conical flask. It's important you mention the correct apparatus here. So you've got your sulfuric acid in your conical flask, H2SO4. Now you're titrating it against sodium hydroxide, and it says that eventually you need 16.7 centimetre cubed of sodium hydroxide. Now you might be thinking, how do I know which I'm going to pipette? Now the pipette is that piece of apparatus which looks a little bit like that, and has a sort of pipette filler on the top there. Now you get all different types of pipette filler, so I'm not going to describe it, but the pipette can only measure one particular volume of liquid. So it's unlikely that you could buy a pipette that measures exactly 16.7 centimetre cubed of sodium hydroxide. That seems a bit of a random amount, okay? But fairly standard amounts, so 10 centimetre cubed, 25 centimetre cubed, 50 centimetre cubed, those sort of rounded amounts, which might crop up quite commonly, we can buy pipettes for. So that's how you spot. It's just looking at the numbers and seeing which is the most obvious, really. That's probably not a particularly good explanation. But we'll use the pipette to put the sulfuric acid in, and then we will put the sodium hydroxide in the burette. Now the burette is that piece of apparatus, a long tube with lots and lots of lines on it, graduated, so you can accurately measure volumes, and it's got a tap at the end to allow you to add liquids very slowly to each other. So we will charge a burette with the NaOH. Now we could start adding the sodium hydroxide. We could start adding the sodium hydroxide from the briquette into the conical flask. But if we did that now, we wouldn't know when we had neutralised all the sulfuric acid. So you need to add an indicator to the sulfuric acid. So you can choose any indicator you like except universal indicator for this experiment. And the reason you can't use universal indicator is because it has a range of colours. So it's very, very difficult to determine the exact end point. In other words, the point where it goes from acidic to alkaline with its range of colours, because it's very difficult to distinguish between light green and dark green and green. So what exact point does it go past the end point? Whereas any other indicator only has two colours. Okay, methyl orange is red in acid and yellow in alkaline, so it's quite easy to see when it goes from being red to when it goes to being yellow. Okay, my personal favourite is phenolphthalein. And you only add 3 drops. Okay, to the conical flask. Now the phenolphthalein, because it's gone into acid, will be colourless at that point. So it is important to think about what colour your indicator would be at the start. You're then going to add the sodium hydroxide dropwise. And you're going to swirl the flask. Okay, and when do you stop adding the sodium hydroxide? When you get a permanent colour change. So the colour change, and you need to know this, so stop adding sodium hydroxide when colour changes from colourless to, now here's where your knowledge kicks in. Do you know what colour phenolphthalein is in alkaline? I hope so. I call it magenta. It's a lovely pinky colour. Now if you've chosen a different indicator, for example methyl orange, the colour change will go from red to yellow, and that's absolutely fine. It just depends on what you prefer. I'm going to pause this video now and we will restart with a volumetric calculation that follows on from this question here.